Hello everyone, I'm Amani Soudi and I've taken the Embedded Systems internship offered by Emertxe in the last month, and I would like to share with you my experience and the topics we covered during this internship, and lastly, the project we were working on. Let's first have an idea of what we will cover in this presentation. So, in the first chapter, we will talk about the background, where we will highlight an introduction, overview and goals of this internship, a brief introduction to embedded systems and its categories, requirements, and components. Then we will talk more about the theory part of the internship in the next chapter, where we will highlight the importance of C language in embedded systems, the C concepts and foundations we covered during this internship, what is a microcontroller, and lastly, the difference between microcontroller and microprocessor. In the third chapter, we will talk more about the implementation of the project, where we will focus on the requirements of the project, its architecture and design, then we will see clearly the project. And lastly, we will talk about the project usefulness, thanking this internship's team, and having a summary of all of the internship and presentation. Let's first start with our introduction. So, during this internship, we explored the world of embedded systems, and it was a practical journey where we learned how things work in real life electronics. And a significant part of our learning was a project where we built a microwave oven. This project was more than just building a kitchen appliance, but it was a chance for us to use what we learned in our course. So we started by designing and programming the microwave oven to do specific tasks. And this practical experience was essential because it helped us connect what we learned in class to real life situations. And also, working on this microwave oven project improved our problem solving skills because the challenges we faced during the implementation of the project made us think critically and come up with smart solutions and skills that are essential in embedded systems. Now, let's talk about the overview and goals of this internship. So, the main aim of this program is to help students like us transition from academic studies to real world electronics industry. So, it prepares us for jobs in exciting fields like IoT, automotive, robotics, which are the future of technology. And this specific program is organized into four distinct phases, and each one is designed to maximize our learning experience. So, in the first phase, we focus on the software development life cycle, which called CDLC, and learn about project requirements. And then in phase 2, focuses on building our foundational knowledge by teaching us embedded C and microcontroller programming, which are essential skills in electronics. Phase 3 is where we put our learning into practice by working on our project. And lastly, phase 4 is all about staying up to date with industry trends and learning how to create impressive resumes through a module called D. Now let's focus more about the content of our internship and start with embedded systems. So, what is embedded systems? Embedded systems are specialized combinations of hardware and software designed for dedicated purposes. So, they operate behind the scenes in devices we use daily. These systems integrate hardware components like microcontrollers or COCs with specific softwares to perform specific tasks and enhance our experience across various applications. Now let's take a look at some devices that use embedded systems. So here we have digital cameras, smartphones, medical devices, and microwave ovens. And embedded systems are all around us in various forms. Some stand-alone devices like thermostats that control the temperature in our homes, digital cameras that capture our precious moments, and printers that produce documents. Also, in real-time situations, embedded systems play a crucial role, such as in anti-locking braking systems that's known as ABS, that help us stop our cars safely, airbag systems that protect us during accidents, and flight control systems that ensure airplanes fly smoothly. We also have networked embedded systems connecting devices like smart home hubs that control our lights and appliances, industrial IoT systems used in factories and industries, and smart grids that manage electricity distribution. In our daily lives, we rely on mobile embedded systems and smartphones that keep us connected, tablets that offer portable computing, and wearable devices like smartwatches that monitor our health and fitness. These embedded systems make our lives easier and more convenient. Embedded systems like the ones we are talking about have some important rules to follow. First, they need to be super reliable, which means they can't mess up. Second, they should be cheap so that lots of people can afford them. Third, they should use as little power as possible so your batteries don't die quickly. Fourth, they should be really good at using their brain power to do tasks. Finally, they need to be smart about how they use their memory to save space. These rules help making sure embedded systems work well and don't cost too much. Now let's take a look at embedded systems components and challenges. Embedded systems face some challenges that we need to tackle. First, they should be good at taking in and sending out information to do their job well. Second, adding a special computer program called an operating system can be tricky. Third, they need to make their code super efficient to save time and power. And lastly, they have to check themselves to make sure they work correctly and fix any mistakes, which can be a bit tricky too. These challenges make embedded systems a bit complex, but we could find ways to overcome them. Now let's talk more about the components of embedded systems. So embedded systems have different parts that make them work. As we can see here in the picture, we have in the middle we have the microcontroller or COC, which stands for System on Chip or microprocessor. So this little computer does the thinking and decision making, and then we have the memory to store information and instructions, and we also have things like ADC and DAC to handle converting real world stuff into digital information and the other way around. We also have chips like VBGA or ASIC that help with specific tasks. And these systems can also have extra things like buttons, screens, or ports, as we can see on this picture. They also use sensors to understand their surroundings and actuators to do things like moving parts. And all of these parts work together to make embedded systems do what they are supposed to do. Now let's talk about why C programming language is widely used in embedded systems. So the C programming language holds a great significance in embedded systems for several key reasons. Firstly, it enables efficient communication with hardware, which is an important aspect in achieving speed and resource optimization in embedded systems. Secondly, its adaptability makes it compatible with a wide range of hardware platforms, rendering it a versatile choice for various embedded applications. Moreover, C boasts precise memory management capabilities, crucial for resource-constrained embedded environments. Its quick execution speed makes it perfect for time-sensitive tasks such as those found in robotics and automotive control. Additionally, C allows direct access to hardware, empowering developers to fine-tune system behavior. Lastly, it offers a rich range of embedded development libraries, simplifying common tasks and making the development. And as we can see here on the pie chart with the title of Key Programming Languages for Embedded Systems, we can see that C is the most used language in embedded systems with a percent of 70. Now let's talk about C concepts covered in this internship. So at first we had an introduction to C and data types, where we talked about basic structure of C programming, data types in C programming, variables and constants. Then we talked about operators and array, focusing on arithmetic operators, relational operators, and arrays. Then we focused on conditionals, constructs, and operators, talking about if-else statements, switch statements, and logical and bitwise operators. And then pointers and functions, talking about pointers and memory management, functions and passing arguments, and returning values from functions. And also we talked about recursion, const with pointer and strings, focusing on recursion and its uses, const pointer and pointer to const, strings, and string manipulation. And story classes, talking about Linux OS memory segments in user space, and memory segments details. And lastly, we talked about preprocessor, focusing on preprocessor basics, header files, object-like macros, and micro arguments. Now let's talk about microcontrollers and microprocessors. Microcontrollers are like the mini computers of the electronics world. They are designed to carry out specific tasks, and they are excellent at what they do. They shine in applications where being compact and efficient is a top priority. However, it's important to know that they do come with certain limitations. For example, they don't have vast memory capacity, their ability to handle inputs and outputs is somewhat limited, and they lack some of the fancy features found in larger chips. But despite these constraints, microcontrollers play a crucial role in making many of our electronic devices work smoothly. Whereas microprocessors are like the all in one brains of computers. Unlike microcontrollers, they are made up of individual components, making them highly flexible but also more complex to work with. These chips offer a wide range of functions and can handle various tasks. However, they might not be as efficient as microcontrollers when it comes to specialized jobs. So, while microprocessors give us lots of options and can do many things, they might not be the best choice for tasks that requires incredibly efficient and accurate details. Now let's talk about the project requirements, its architecture and design. For our microwave oven project, we needed several important tools and components to make it all work. So first we use the MPLAB ID, which is a software that helped us write and manage our program. Then there's the XC8 compiler, which is a tool that turns our written code into something the microwave can understand. Now let's talk about the Bixum lab. So inside of this lab, we use a special chip called BIG16F877A, which is like the brain of our microwave, and it helps us control everything. We also use a tactile switch, which is those buttons you press on your microwave to set the time and start cooking. And there's a 16 by 4C LCD, which is like a little screen that shows us what's happening inside the microwave. We also use a mattress keypad, which lets us type in how long we want to cook our food. And lastly, we use timer 2, which is our timer that keeps track of how long our food has been cooking. So with all of these tools and components, we were able to create a super cool microwave oven that works just the way we want it to, and that we will see in just a moment. And here we also have the Bixum Lab architecture, where we have the microcontroller in the middle, which is BIG16 F877A. We also have the I2C, which helps our components share information and work together. We have also the RTC, which stands for real-time clock, or the EEPROM, which help our microwave remember important settings. We have also the LM35, which is the temperature sensor, which checks how hot our food is getting to make sure it's cooked perfectly. We also have the RS232, which allows our microwave to connect to other devices or systems like a computer. We have also the GPIO, which stands for General Purpose Input and Output, which can do different tasks like turning on the fan or controlling the light inside. We also have the LCD, which stands for Character LCD. This is our microwave's display screen. It shows us what's happening, like the cooking time or the mode we have chosen. We also have the ADC, which stands for Analog to Digital Converter, which takes measurements from sensors like the LM35 and turns them into numbers that microwave can understand. We also have the buzzer, which is like a little alarm that make a sound to let us know when our food is ready. We also have the LEDs, which light up to show us what's happening, like when it's cooking or when the timer is running. We also have the digital keyboard, which help us control our microwave by pressing the right buttons. We also have the SSD, which stands for 7 segment displays. Its displays show us numbers to allow us to set the cooking time and see how much time is left. And lastly, we have the Matrix keypad, which is like our microwave's keyboard. It's a grid of buttons that help us input settings and interact with our microwave. Now let's talk about the project usefulness. So our microwave oven project is really helpful because it makes heating food super easy. You can use micro mode for regular cooking or grill mode for meat and bread, and convention mode helps you heat up the oven quickly. We learned a lot by making something that is so common in our daily lives, and it gives us an edge when we want to work in the electronics industry. We figure out how microwaves and their mode works, which is cool. And now we want to say a big thanks to our teachers who helped us during this internship. These teachers and mentors played an important role in helping us learn and grow in our journey into the world of embedded systems. Their expertise and guidance were invaluable, and we are grateful for their help. Throughout this internship, we have embarked on a remarkable journey that has equipped us with invaluable practical skills, laying a strong foundation for our future careers in the electronics industry. One of the standout accomplishments of this program is our implementation of the microwave oven project that serves as a shining example of the incredible advantages offered by embedded systems. This immersive experience has not only expanded our knowledge but has also given us the confidence to tackle real world challenges in this field. As we look back on this transformative journey, we are excited about the promising opportunities and fulfilling careers that lie ahead in the dynamic realm of electronics. And here's our Bixim lab with BIC16 F877A microcontroller. Here we have our 7 segment displays and our matrix keypad and our LEDs, the LEDs of port B and the LEDs of port D, and then our cooler, buzzer, heater, and also our serial. And lastly, we have our reset button, which when we click it, we will reset the whole program. So let's power our program. So here we have 4 modes: the micro, grill, convection, and start. Let's start with our micro. So here it's showing the power is 900 watts, and we have to set the timer. Let's choose 10 seconds, and we have to press the enter. For entering, we have to press the hash, and for clearing, we have to press the start. Now let's press hash to enter. As you can see, the fan is working. That means our microwave is working. And here it's showing time's up, which means the heating is done. Now let's try the grill mode. And here also we have to set the timer. Like it's the same as the micro mode, but in this mode we don't need the power of 900 watts. And let's choose 10 seconds and enter. And now our food is ready. And now let's choose convection mode. And here we have to choose the temperature. Let's choose 50 and press enter. Here we have the time remaining. And it finished. And after that we have to set the timer and enter. And we can pause the timer by clicking on 5. And we can start it again by pressing 4. And lastly we have the start mode. And in this mode we have in default 30 minutes in the timer. And if you wanted another 30 minutes we can click on start. And we can press 6 to stop our timer. And that is our microwave oven project.